Let's now train our model using a pre-trained Word2Vec embedding. We shall also be using TensorBot to project these embeddings. So we're going to include the TensorBot plugin projector, and as usual we'll load TensorBot. The pre-trained Word2Vec layer or embeddings we shall be using will be from the GenSim library. That's why we import the GenSim downloader, which will permit us load or download this in case where we haven't yet downloaded it. But when we've downloaded already, once we just simply load it each time. So here we import the GenSim downloader as API. Run this. This pops up because we had already loaded this, so let's reload. Okay, that's fine. Note that GenSim, you have to install it, so you just have to say pip install GenSim and you get that installed. Now that's done, we are gonna load the embeddings. The specific embeddings we're loading is this Word2Vec trained on Google News dataset and with an embedding dimension of 300. So let's load this. Once this has been loaded, we could see here, for example, index to key. We take the zeroed index. There we go. So we go from this. We could have this index, and there's the corresponding word for this index in the vocabulary in which we're working with. Now let's look for the length of the whole vocabulary using this index to key. We have len, and that's it. We have a 3 million vocabulary data set which has produced this embeddings. So what we have here is this embedding which takes in 3 million different words, and then from these words generates a vector in a lower dimension, or rather a vector of lower dimension in the lower dimensional space of 300. So we're living from 3 million now to 300. So that's it. We could also get for a particular word this index by using the key to index. So we'll take key to index, we specify the word, say day, see that's this index. We could say and, that doesn't exist. Actually the way and exists in this vocabulary is with the caps. So that's it, the 169th index. This means if you want to get the feature vector of n, all we need to do is to take this wv and specify 169, and we'll run that, and there we go. We could take in that shape. So that's it. We have this 300 dimensional vector. Note that unlike previously where we were generating our own vocabulary, in this case the vocabulary is already built. This means that if previously, for example, they corresponded to the position say 5, now that they corresponds to the position 169, you see that we can use this same vocabulary we had here in working with a model or with this embedding layer which has its own different vocabulary. So it means we have to restart the data preparation process again, because we are going to use this vocabulary provided by GenSim's Word2Vec Google News 300 layer. Still we have the pre-processing, so we'll just simply have this. We have the pre-processed sentences. Let's take this off. Take this off. And then also you may have noticed that when we had this word to index, actually key to index, when we had a key to index of say and, it doesn't exist, whereas and in this form actually exists. So that's why we need to rewrite this word to index function, which is defined such that firstly we limit the vocabulary size. So in this case our vocab size, we could define this here. We have a vocab size of 30,000. So instead of having the vocabulary size of 3 million, we're working with the first 30,000 words in the vocabulary. And that is why if we take in a word and we find the index, the corresponding index to that word, if it's less than 30,000, we return the index, and if that index is greater than or equal to 30,000, then we return 0, saying that simply that word doesn't belong to the vocabulary. Now another problem arises when we have, for example, a word which actually belongs to our vocabulary like and, but which doesn't belong in the exact form in which we are inputting it. Like when we have we saw with the and, that was a key to index of this and, we see that, and this gives an error. So this means what we have this as and actually belongs to the vocabulary, but not in this exact form. And also one thing to notice that generally after pre-processing, we're going to have this form instead of this. So what we have to do is we are going to use exceptions. Now what goes on here is we first of all try. Now if it matches, we return out. If it is greater than 30,000, we return 0. In the case where we have, for example, this and where there is this error, what we do is we get into the exception. Now that we get into the exception, we are going to modify this input word such that this first becomes a capital letter. So like this, we have the word 0, that's the first character, like in this case here. If we let's take this off so we could understand what's going on. Take this off, print this out. We have this. Suppose we have word equals and. So you run that, it becomes this. Now obviously if you have and, it's going to remain the same. So what we've simply done here is we've taken the first, we've made it a caps, and then we've taken the second character up to the end, that's this, and then added it up to this modified first character, and that's how we obtain this. So that's why we do this here. So instead of doing the key to index of and itself, we do key to index of this and instead of this. Now once we do that, if still this is part of the vocabulary, we return it. If not, we return 0. Now in case there is an error which comes up here, we just simply return 0. And so that's how we modify the key to index to suit our problem. Could take this off now. Let's now go ahead to prepare this data. So we go through one round, that is actually picking one review from our data set. Now for every time we get into this loop, we want to do this twice. The first time for the positive review for a positive review, and the second time for a negative review. So we go for t in the range 2. If t is equal to 0, the positive review. When t equals 1, we have the negative review. So right here we simply load this. Now we could print this out. So let's comment all this like that, and then let's print out what we obtain after this. Print out the review, run that, and that's it. We have this first review, and then we also have this review right here. Now that we get this review, the next thing to do is, based on this vocabulary which is provided by this Word2Vec Google News 300 of GenZim, we are going to take each of this word and then link it up with its corresponding index. So like for example, if we have key to index of say I, you see that's it. We want to have this index of say went, we have that index of and. You see that this is going to pose a problem, but we've solved this with this word to index right here. So basically that's what we're going to do. We're going to take each of these words and then get their corresponding indices. For the next step, let's uncomment this part. We define this review list, and then we are going to enumerate through the list made of these different words. That's because we've gone through this strings.split. So obviously we're gonna have this all these different words, and then for each word in this here or in this list, we're gonna pass this, because this is the word and then this is the index. So like we could take this as word, and then we have this word. That's fine. Now this is the index. Actually, here's the index. Okay, so we have the word. So for each word, we are going to pass it into the word to index, which we've defined here. So for each of these words, we convert the word into a string, and then we take the values from the second position to the second to the last position. Now let's print out this so you could understand exactly why we're doing that. So let's have here a word. We'll run again. Okay, now notice that once we have this word, this is exactly what we get. So we have this each and every word which goes in here. So that's it. We have these different words right here. Now when we do string of this, that's when we have the string of this word, the numpy. So if we convert this string of word the numpy, because they are tensors. So if we take that, this is what we get. Now to eliminate this, we take from the second position to the second to the last position, or from the third position, which is actually this, to the second to the last position. So we have 0, 1, 2, this position, to this position right here, and that's what we do everywhere. So basically that's why we do this right here. Now once we have this exact word I, we pass it into word to index, and then it gives us the index. If this index here, now let's differentiate this, let's maintain this at I. So we have that if this I is greater than 250, in this case here 250 is a sequence length. It means that we can't have a review which is greater than 250, and in the case where we have a review which is less than 250, we just simply pad it. In the case where it's greater than 250, we simply crop it from the point where it gets greater than 250. So that's why we have here, if we have this, we simply break. And then later on here, we are going to concatenate what we get from here, that's this reviews, which is basically this, with zeros, where the zeros have a length of 250 minus the length of the review. So in the case where this length of review is, or this reviews less than 250, we're going to pad it such that this output right here, let's uncomment this. So here we could print out the output such that this output right here gets a shape of, or a dimension of 350. And the case where it's greater than, we are going to obviously have directly this, which is going to have a shape of, or dimension or length of 250, because from the point where we get to 250, we get out of this loop. So let's print this out. Let's take this off, run again, and there we go. We see that we have the shape. Let's take this out, off, and run again. There we go. So that's what we have. Now for the positive review, we see the patterns. For the negative, we see the patterns. Now that we have this set, we could close the file. So we'll close the file, and then we take this and pass into X. So that's it. In the case where t equals 0, that is when it's a positive review, y is 1. In the case where it's a negative review, y is 0. So run that, and there we go. We now have this 1 and the 0. We have the X and then the Y's. So that's it. We could take this off and then build a generator. Yes, I did a generator which basically uses what we just defined. So but with the difference that we have now this batch size, so we're going from this to this. Let's run this data generator. We add some constants. Here we have the train directory for the positives, train directory for the negatives, validation directory for the positive, validation for the negatives, the batch size, learning rate, the number of epochs. We could take this to 100, the vocab size, and then the sequence length. We'll run that. we now call we create the train and validation generators. Yeah, let's take this off. Val, and we have val pose and then val negative. The vocab size defined, sequence length, byte size, vocab size, sequence length, byte size. Just as with this. So we run this and run that. The next thing we shall be doing is defining the embedding matrix. Right here we have this empty embedding matrix list. Then we go to the vocab size, and for each element or each word in the vocab size, we get its corresponding 300 dimensional vector, which is gotten simply by calling the WV that we defined previously, which is this. So we simply call this right here, and then we get that 300 dimensional feature vector. Now once this is okay, we now convert, let's take this off, we convert this into a numpy array, and then we could print out the embedding matrix shape. In the case where we had say 3 million, or let's say a million, if a vocab size is a million, then we shall have a million by 300 dimensional matrix. We set this back, vocab size, run again, and that's fine. Now the next thing to do for the modeling is we define our embedding layer. Now as usual, we have this inputs, which has the shape, sequence length, which is 250. We define our embedding layer. It takes in the vocab size, and then it takes in the embedding dimension. So here the vocab size, as we've seen, is 30,000, and here is 300. Then we have this embedding initializer, which is simply the embedding matrix. We also have this very important step where we set this embedding layer to be untrainable. So we have defined this trainable to be false, such that whenever we get a word, it simply generates the feature vectors from that word without having to retrain this again, because this has already been pre-trained on some data. Now after defining this, we have to include our embedding layer. We have conf1d max pool, conf1d max pool, global max pool, and then the dance layer, specifying the activation to be sigmoid. Run this. There we go. We have this 9 million non-trainable parameters and about 200,000 trainable parameters. This 9 million could be obtained quite easily. We have 30,000 times 300. So that's how we obtain the 9 million parameters, because basically it's just the metrics which we've defined. Now once we have that, we have the remaining 200,000 parameters. You could always increase this depending on the exact problem you're solving, or you could also reduce it. So that's it. We take this off, and then we go to compile our model. We define the binary cross entropy loss, the optimizers Adam, the matrix accuracy, and then we are in graph mode. Run that. The next thing to do is we fit our model. So right here we have this conf1d pre-trained embedding.hdf5, which we define as our checkpoint. We have the model checkpoint. Could add this here. Callback. We also have the tensor bar callback, which we define right here. We specify the log directory, and then the frequency equal 1. So that's it. Let's define the log directory right here. We run this now, and we'll simply start with training. While the model is training, let's set up a projector. Right here we're gonna make a new directory for the log dir in case it doesn't exist yet. Then in this metadata.tsv file, we are gonna store for each index and its corresponding word in the vocabulary their values for every line in this metadata.tsv. This means that, for example, we could have the first line, we have 0 like this, the next line 1, let's say day, 2, let's say off, 3, let's say let's say U, and so on and so forth. And the reason why we're doing this is because we are doing projections in the lower dimensional space, and we want that when visualizing we are able to see each word which is with its corresponding vector in the smaller dimensional or lower dimensional space. So that's why we actually have to do this like that, and then for every word its corresponding index. Now we also know that these indices are linked to their corresponding vectors. So that said, we have also this embedding weights. Here we get from the model this is actually the embedding layer. So when we pick out the zeroed layers, the embedding layer, we get a weights. It gives us this embedding weights here, which happens with the embedding metrics. Then we pass it out into this TensorFlow checkpoint. Now once we have this checkpoint, we now save it in this embedding.ckpt file or embedding.checkpoint file, such that for every word we have the corresponding feature vector stored in this embedding.checkpoint file. Once this is okay, we now define this projector config, then embedding. With the embedding, we define as metadata path, which happens to be the metadata, the TSV file we had defined previously, which contains all this information. Then once this is fine, we have this log directory and the config passed into the visualize embeddings method. And all we left to do now is just to call on TensorBot. Let's take this off, and there we go. For now, let's wait for the model to train.
Now you have a bunch of three-dimensional embeddings. So each of these is a 300-dimensional.
We actually trained for just one epoch. We're supposed to have
what
this.
was then
Yeah.
the target for the softmax
So
training would be
now
that
let's
it should
run
predict
this.
that the word juice was what came out.
After
this.
running that, here's
So this hidden
the
layer here
folder
will have its own
which has been
parameters. Or
created.
have some,
This folder
we're
right
gonna call
here.
this W1.
And this is the
There's also
metadata.tsv
B1. The
file we're
softmax
talking
layer with
about.
its own
So
parameters,
as you can
W2,
see, we go from
B2.
0 to
And if they're using 300-dimensional word embeddings, then here we have 6 words. So
different words.
this would be
So clearly we could see that we have its
6
index
times 300.
and its corresponding
so this
word.
layer or this
Then
input
in
would
this
be
right here, it contains the embedding weights. So with that, we also have
what's
the
actually more
projector
commonly done is the
configuration
you always
file,
want to
which is
predict the
this
next word
with the metadata
given,
path
say, the
specified.
previous.
Take
So
this
this is
off.
how you adjust either
And
very
then
long
we
or
could
very
go
short
ahead and
sentences.
run
Where you
this.
decide to always just look at the previous 4
And there we
words.
go.
So you say,
Here's what we
I'm just going to use
obtained.
those 4
We have
words.
the epoch accuracy,
And so,
epoch loss.
let's
We
just
see
get rid
the
of these.
accuracy and the loss value.
And so if you're
Let's take
always
this
using
off.
a
This is
4-word
the
history,
last
this
thing
means
we
that your
did.
neural
So
network
we
would
take that
input
off. We have the accuracy
a
and the loss
1200-dimensional
value that we could see
feature vector,
basically
go
from
into
this
this layer,
here.
then have a
And
softmax
apart from
try to
that,
predict
we
the
also have the
output.
graph.
And again,
Here
variety of
graph
choices.
compared to what we saw last time.
And using a
this
fixed history just
way
means that you can
simpler.
deal with even
So here we
arbitrarily long
basically have
sentences.
this embedding.
Because the
After the
input size
embedding,
is
we
always
have
fixed.
this conv1d,
So the
max
parameters
pool,
of this
conv1d,
model will
max
be
pool,
this
global
matrix
max
E,
pool, and then the
and
dance
used to
layer.
be 4 words. It's the
So
same
open
matrix
this
E.
up. See,
And then
basically that's
these weights are also parameters
then
of the
let's take
algorithm.
this,
And
let's
you can
reduce
use backprop
this.
to perform gradient descent to
Then
this
we
algorithm.
now get
will
to
learn
the
pretty
projection.
decent word
So let's get
embeddings.
to the
And the reason
projector.
is, if you remember
And we
orange
actually
juice,
have 2 runs.
apple juice example,
Yeah, this is the last run.
orange and
So
apple, because
let's
doing
run
so
this. This is the run
allows
we
it to
did, yeah,
fit the
this
training
one.
set better, because it's going to see
As you
orange
can
juice
see, we're
sometimes,
computing
it'll
the
see apple juice
PCA.
sometimes,
We're going to see exactly
a 300-dimensional feature vector to represent all
PCA
of
stands
these
for
words.
principal
The algorithm will
component
find that it
algorithm.
fits the training set
So
best.
that's
if
fine.
apples,
Now,
oranges,
we notice that
grapes, and
we
pears,
are
and so
actually
on. And
visualizing
maybe also
this different
durians, which
points
is
in
a
a
rare fruit, end
three-dimensional
up with
space
similar feature vectors.
instead of a
So this is one of the earlier
300-dimensional space.
and
Talk less
pretty
of a
successful
3
algorithms for
or a
learning
30,000
word
dimensional
embeddings, so
space.
learning this
So what goes on
matrix
here is we left
E.
from 30,000
But now let's generalize this
to
algorithm and see how we
300
can derive
dimensional,
even simpler
and then
algorithms.
thanks to
So
the
I want to
PCA,
illustrate the
because
other
with this
algorithms
we use the
using
embedding
a
metrics to
more complex
live from
sentence
300
as our
30,000 to
example.
300
Let's say that
dimensional.
in your training set you have this
Basically,
longer
when we
sentence
pass a
and one
word,
glass of orange
it
juice
gives
go
us
along with my
these features in
cereal.
this 300 dimensional
So what we
space.
saw in
Now,
the
using the
last
PCA
slide was that
algorithm,
the job
we are
of the
able to
algorithm was to
obtain
predict
this
some
in a
word juice,
3D space.
which I'm going to call
The reason why we're doing this
word,
is because visualizing
and it
the
was given
300
some
dimensional space isn't
context,
possible on our screen, so
which was the last
PCA
4
helps
words.
us visualize this in
And
3D.
so
We could also
if your
take
goal
out the
is
third
to learn
dimension and
a
visualize
embedding,
in 2D. As you can
researchers
see
have
here.
experimented
So
with draw
this
for the
is
context
a
to be a
2D
few words right
visualization,
before the
or
target
even
word.
though
But
normally
if your goal isn't to learn the language model
we could
per
also
se,
go to a
then you can choose
1D
other
visualization,
context.
but
For
that is
example,
going
you
to
can pose a
give
learning
us much
problem
information.
where the context
So
is
with
the 4
this,
words on
we
the
have
left and
our,
right. So you
let's
can
take
take
this
the
back.
4
We have our
words on the
3D
left and
visualization.
right as the context,
back.
and what it works, similar to
Then
what you saw
we could also
in
do
the
the
previous slide,
TSNE, that's
to
the
try to predict the
T-distributed
word in the middle, try to put it to be a
stochastic
target word.
neighbor embedding.
That's just one
This is
word
the
later.
UMAP.
Or you might choose 2 words before. So
We could
you
also
have another
define a
pair
custom
where a
transformation.
target could
So
be
for now, let's work with a PCA.
glass.
So you can see here
Or
we have this points
maybe just
now
by chance
in this
a plus minus 10
3-dimensional
word
space.
window, or
So
plus minus
there
5
we
or
go.
10
We
word
have
window
our vectors.
of that input
But
context
what we're
word.
getting for
And
now
obviously this is not a
just
very easy
the
learning problem because,
indices
you know, within
and their
plus
positions.
minus 10 words of
So
the word
like with
orange, it
this,
could be a
there's a
lot of
position
different
of
words.
18,000.
But the goal of setting up this
454th
supervised learning
index.
problem isn't to
There's a
do
position
well
of,
on the
for
supervised
example,
learning problem per se. It is that we want to
value,
use this learning
for
problem
example,
to learn good word embeddings.
7,000.
So here are the details of the model. Let's say that
Now,
we'll continue,
what we need
but
to
the
do
basic
to link
supervised
this
learning problem we're going to
words
solve is
by
that we want to
simply
learn a map which we're going to call T,
loading this
which
file
might
right
be the
here.
word
So we're going to
juice,
file,
or the word glass, or the word my.
and then we choose
if we use the
the,
example from
let's get back
previous
here.
use, word map of
We choose
10,000
this
words.
metadata
And so that's
.tsv
the
file.
input X that you want to learn to map
Loading.
to that output
Get out
Y.
of this.
So to
As you
represent
can
the
see now,
input, such as the word
since we're
orange,
using the
you can start
metadata
off with
.tsv
some
file,
one hot
each
vector,
index
which
is
can be
linked to
write
the
as O
corresponding
subscript
word.
C.
So
So
now
there's a one hot
we
vector
have
for
the
the
words
context
projection
word.
in our
And
3D
then similar
space.
to what you saw in the last
You see
video,
that we
you
came
can
from
take the
30,000
embedding matrix
dimensional
E,
space,
multiply
300
E by the
dimensional,
vector O
and times the
subscript C,
PCA,
and this
we get
gives
into a
you
3D
your
space.
embedding vector
Now
for
let's
the input
look at
context
this.
word.
Let's
So here,
explore
EC is
more
equal
about
to
this space.
capital E
If you
times
take a
that
word like
one hot
to love,
vector.
as you can see
Then
here,
in this little neural network that we'll
love
form, we're going
is
to take this vector EC
746th
and
index.
feed it to
Then we
a
use the
softmax
cosine
unit. So I've
similarity
been drawing
to find
softmax unit
its
as like a
100
node in a
closest
neural
neighbors.
network. That's not an O,
Number
that's
of
a
neighbors, simply
softmax
here.
unit.
Let's
And then it's the job of the
say
softmax unit
180.
to
So we have
output
that. Now as you
y
can see,
hat.
the nearest points
So
the
to write,
original
this is the
space,
model.
we
The
have
softmax
love,
model
love,
estimates
passion, hate,
probability of
loving,
different target words
affection,
given the input
longing,
context word
romance,
as
joy,
E
friendship,
to the
wonderful, devotion. And as
theta
you could see,
T
all these words
transpose
are very similar to the word love. We could take
EC,
another word, say July.
right, divided by sum over all words, and we could say sum from j equals 1 to all 10,000 words of e to the theta j with
May, March, June, July,
output t.
So
With really lots of chance of a particular word t
our embedding
being
layer,
the
or the
label.
pre-trained embedding layer, is doing a great job in linking the words.
So I've left off the
to
bias
future
term
vectors,
in this, could
as
include
words
that
which are
too
highly
if we
related
wish.
are very close to each other. There is a cosine.
And then finally, the
already,
loss function for softmax will be the usual. So we use y to represent the target word, and we use a one hot representation for y hat and y here. Then the loss will be
cheers, thanks, daddy,
the negative log likelihood. So sum from of
and all of that.
yi
we see how we are able to use tensor
so that's a usual loss for softmax.
Visualize
see less frequent words like durian much less often. This is okay if they're buried deeper in the tree because you don't need to go that
Let's now go ahead to do some testing.
Various heuristics
here we have
for building the tree that you use to build a
positive
hierarchical
review and a
softmax
test
classifier.
negative review. This movie is very interesting.
So this is one idea you see in the
The
literature
actors do a
for
good
speeding
job
up
in
the
showing how people
softmax
lived in the 18th
classification.
century and how they managed to carry out their daily activities.
But I won't spend too much more time just, and you can read more details of this in the paper that I referenced on the previous.
And the actors were tired. These two reviews aren't in the
but I won't spend too much more time on this because in the next video we'll actually talk about a different method called negative sampling. which also works really well for speeding up the softmax classifier, and the problem of needing to sum over the entire vocab size in the denominator.
We pre-process it.
So you see more of that in the next video. But before moving on, one quick topic I want you to understand is how to sample the context C.
Doing this,
so once you sample the context C, the target T can be sampled within, say, a plus minus 10 word window of the context C. But how do you choose the context C? One thing you could do is just sample uniformly random from your training corpus. When you do that, you find that there are some words like the,
so this is what we have as input.
And
then
to, and so on, that appear extremely frequently. And so if you do that, you find that in your context to target mapping pairs, you just get these types of words extremely frequently. Whereas there are other words like orange,
so we see that
apple,
with a negative review, we clearly
and also
have
durian, that don't appear that often. And maybe you don't want your training set to be dominated by these extremely frequently occurring words, because then you spend all practice the distribution of words PC.